Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, we will apply one method to find the probability distribution for a function of random variables. The method that we're going to discuss in this video is the distribution function method. Okay, let's begin. So, that is the problem that we're going to be tackling today. We have a uniform distribution, that's our original random variable, y, but then we transform that variable. The transformation is going to be given by -2 times the natural log of y. And what we want to show is that by transforming that uniform random variable that way, right, we end up with an exponential distribution with mean 2. Okay, so what's the idea behind the method of distribution functions? Okay, let me just go back for a sec and refer to our lecture notes from chapter 4 and remind you the relationship there is between the PDF, the probability density function of a random variable, and its CDF, the cumulative distribution function. Okay, so it turns out that if you take the derivative of the CDF, then that equals the PDF. Okay? Well, that's the main idea behind the method of distribution functions. What we're going to be doing is we're going to be finding the CDF, okay, the cumulative distribution function of that transformation, okay, and once we have it, we are going to take the derivative, and that is going to give us the PDF. Okay, and if we're lucky, like in this example, then that PDF will have a form that we're going to be able to recognize. And sometimes it's not going to be one of those popular probability distributions, okay, in some cases, but still that is going to help us find the PDF, if it's a continuous random variable, right, of the transformed random variable that we're interested in, like W. Okay, so one of the main things we have to pay attention to when applying these methods is we have to find the possible values that W, the transformation, will assume. Okay, so let me make a quick graph first, and then we're going to do a little bit of math to determine what are the possible values for this transformation. Okay, so I will launch R. So we're going to create a sequence that starts at 0.0001, right? Remember that the y's are between 0 and 1, but without including either 0 or 1. So I'm going to be creating a sequence of numbers between 0 and 1 that look like that. Okay, and then W, we know, is given by -2 times the natural log of y. Note that again, maybe we have done this before, but let me point that out, that in R, right, log means natural log, because the default base is e, okay? So now let's plot this guy. If you want a scatter plot, if you want to create a graph, first the syntax of that function plot is you place the numbers that go on the horizontal axis, the x coordinates, and then the ones that go on the vertical axis, the y coordinates usually. But in this case, the number that goes on the horizontal, well, the numbers that go on the horizontal are the numbers contained in that vector y, and then the numbers that go on the vertical are the ones contained in that vector we just created, w. Okay, so LTY is telling R what kind of line we want. In this case, I want a dashed line, and I want that guy to be blue. Let's see. Well, in this case it gave me points because I didn't say what kind of line I wanted. So with type equals L, I'm going to have a line. Okay, that's better. So as you can see, right, that transformation W seems to be always greater than 0, okay, which makes sense from what we know about the natural log, okay. Now let me go back here. So note that y lives between 0 and 1, right? So since y is less than 1, right, that implies when we apply that transformation, natural log, we know it's an increasing function, so that inequality is preserved. But natural log of 1 is what? 0, right? Okay. So, and then once we multiply by -2, the direction of the inequality will change. But that guy, -2 times natural log of y, happens to be our w, which means that w is greater than 0. Okay, so those are the possible values of our transformation, right? We have seen this in a graphical way and using these inequalities. Okay, and it has to be greater than 0, so the natural log function is defined. So okay, so now we have what the possible values are. And as we said, the idea behind the method of distribution functions is finding the CDF, the cumulative distribution function of the new random variable w, right? And then we're going to be taking its derivative and we'll have the PDF. Okay, as you know, CDFs must be defined from -infinity to infinity, right? And PDFs too, but we know that sometimes PDFs will be just be non-zero over a particular region of the whole real line. Okay, but still we have to provide the entire expression, not just the non-zero part. Usually it's a good practice. Okay, so anyway, let's take care of the first case. Case 1, right? What happens if W is less than or equal to 0? So let's find the CDF in that case. Let me start like this, just negative, right? So we use that capital F notation for the CDF, the cumulative distribution function, but we know that that represents the following probability: the probability that the random variable W is less than or equal to a particular value, lowercase w. Okay? But we know that the values that are assumed by this transformation are always positive. So for instance, the probability that minus 2 natural log of y is, say, less than -3 is 0, right? Okay. Okay. So, and we'll go back to this, right? We'll slightly modify this in a sec, because we have to take into account what happens when W equals 0, right? So, can this guy be 0? W? No, right? So, okay. Right? Minus 2 times natural log of y cannot be 0. Make sense? Okay, so first case, when W is less than or equal to 0, the probability of that, the probability that uppercase W, the new transformed random variable, is less than a number that is negative, is 0. So that's the first case. Now, the interesting case is when we have W, a particular value for the transformation, that is greater than 0. Okay? Here we go. Let me copy paste this. This is going to be the same. So, in that case, what's the idea? How are we going to proceed? Well, just like before, we have that the CDF of W is deep down the probability that the random variable W is less than or equal to some number. Okay? So, but now what we're going to use is the fact that W happens to be -2 times natural log of y, the original random variable, less than or equal to some number. Okay? So what do we do next? How is this going to help us? Well, the thing is, we know the distribution of the original random variable y, right? So what we're going to try and do is solve for y, right? Express this event in terms of y, and then use the information about the original random variable y. Okay? So that event, the probability that minus 2 natural log of y is less than or equal to some number w is equivalent to this. Let's divide by -2 on both sides. Okay, so if we do that, let me copy paste this. Right? But by dividing by -2 on both sides, then that inequality will change. Okay? Now let me write this down in a nicer way. So W, okay, right? So what we did is we divided by -2 on both sides, and that changed the inequality. Now let's apply the inverse of that function. Okay, and since you know, natural log is an increasing function, right? It's a one-to-one transformation, and it's increasing, so the inequality will be preserved, right? The direction of the inequality is not going to change. So I apply E on both sides, and then what I have is on this side, I could write it down like that. That's one way of expressing it. You know, an equivalent way of writing that down would be this: the probability that y is greater or equal to e to the negative w divided by 2. Okay, it's just notation. Okay. Now we're making progress, real progress, because we know a lot about y. We know that y has a uniform distribution. Okay, so remember, right, that it would be useful to have the CDF of the original random variable, right? Why? Because we know that at some point we want to take the derivative of the CDF of w, and that is going to give us the PDF, right? But the thing is, if we find the CDF, if we write that in terms of the CDF of y, if we take the derivative, then we're going to have the PDF of y, and we are going to be able to use that information. So let's rewrite this in terms of the CDF of y. So this is the same as 1, that the probability that y is greater or equal to e to the negative w divided by 2 is equal to 1 minus the probability that y is less than e to the negative w divided by 2. You guys agree? Now, let me just argue something. That this is the same as this. The probability that y is less strictly than e to the negative w divided by 2 is the same as the probability that y is less than or equal, right? Why is that true? Well, because y is a continuous random variable. That's why this guy is not going to affect. Okay, now this is just the definition of the CDF of y, right? The probability that y is less than or equal to some number. Okay, so this guy here is just the CDF of the random variable y, the original one, evaluated at that point e to the negative w divided by 2, right? So what we have established here is that the CDF of my new random variable, of our new random variable w, is just 1 minus the CDF of the original random variable y. And that is useful because we know what the distribution of y is. Right? Okay. Now, what we're going to be doing is this. Let's take the derivative with respect to, the random variable of interest. Okay? So, let's take the derivative of these guys with respect to w. Derivative with respect to w by taking the derivative of the CDF of w, we end up with the PDF of w here. We have the derivative of this guy, so derivative of a sum of derivatives, that's the derivative of a constant, that's 0. Then we have a constant that multiplies a function here, so that's going to be -1, okay, times the derivative of the CDF of y, that is going to be the PDF of y evaluated here, and then we have to apply the chain rule. We have to compute the derivative of e to the negative w divided by 2, right? So that we know is just taking the derivative of an exponentially something nice, because we know that is just e to the something. Oh, derivative of e to the something is e to the something times the derivative of the something, right? So in this case it's going to be e to the negative w divided by 2 times the derivative of the exponent with respect to w, which in this case is just going to be -1/2, right? So let me write that down here, -1/2. Okay, so now let's do the math. Let me copy paste this, it's going to be useful. So minus times minus, that's going to be a plus. Let me borrow that guy. So it's going to be 1/2 times the PDF of this guy, of the uniform 0,1 evaluated here, times e to the negative w divided by w. We're almost there. Now let me just point something out. The PDF of uniform 0,1, right? You guys remember what it looks like? So it's going to be, right, it's a uniform 0,1. So the PDF is just a flat line, a constant 1, in the interval 0, 1 and 0 otherwise. Okay? Another way of seeing this is taking a look at our table from our textbook, if you don't remember that expression of the PDF of a uniform. Give me just a second, I'll find it for you. Okay, I'm back. I found that table. Remember that on page 837 you will find this, right? In this case you have the most popular discrete distributions, and on the next page you will have the most popular continuous distributions, among them the uniform. So since we're talking about a uniform over the interval 0, 1, it's going to be 1 over 1, which is just 1, right? If the random variable, if the number y, if the random variable is between 0 and 1, right? Okay, so what we have here, let me write this down. F of, since we have two random variables here of interest, I am going to be very, very specific that the PDF of y, the original random variable, is 1 in this case if y lives between 0 and 1, and this guy will be 0 otherwise. Now, something more. Let's say something about e to the negative w. Do you guys remember what w represents in terms of the original random variable y? The transformation is minus 2 times natural log of y. Okay? So this is the same as this, minus times minus 2 natural log of y. Divided by 2. So that minus times minus is going to give you a plus. And then you're going to have a 2 that is multiplying and a 2 that is dividing. So you have e to the natural log of y. But e is the inverse of natural log of y. So this is just y, right? So it turns out that this expression here is equivalent to just f of y evaluated at y, right? But it turns out that, you know, f of y evaluated at y for a uniform 0, 1 is just 1. And we are applying that here. So what we have is just 1/2 times e to the negative 2, e to the negative w divided by 2, right? And that will be our PDF, and we know that we are applying this for positive w's. So going back to our table, that's just the PDF of an exponential with parameter beta equals 2, right? And that is exactly what we wanted to show, right? And by the way, also from that table, we have the expected values, right? So yeah, the expected value of an exponential is beta. So let's just point that out. Clearly, W has an exponential distribution with beta equal to 2. And we're done, right? Let's summarize what we did here, okay? So what we talked about in this video was one method of finding the distribution of a transformation of a random variable, right? What's the main idea behind that method? This, the relationship between the PDF and the CDF, okay? If you take the derivative of the CDF of a continuous random variable, okay, then you will obtain the PDF, okay? So, and the other idea is, hey, apply the definition of the CDF, meaning the probability that the random variable W, where W is your transformed random variable, right, is less than or equal to something, right? And then write that in terms of the original random variable Y, right? Find that in terms of the CDF of the original random variable Y, right? Find that CDF, take the derivative, and that's it. Okay? And note also here, we have to be careful with the values that this W assumes. So in this case, the non-zero part of the PDF is this, right? The PDF of W will be an exponential for W that is greater than 0, and it's going to be 0 otherwise, okay? Which is, again, exactly the definition of an exponential PDF. Well, that's it for now. Thank you so much for watching. Please keep working hard and take care. Bye.